Hello there. In this video, we're going to be confirming the results of Professor Doru in her video regarding the minimization of the perimeter of a rectangle while maintaining the given area that we started with. So in order to do this, let's just begin by kind of refreshing on what was done in the problem initially. So we were given an area, or excuse me, we were given a rectangle of some given area A and dimensions x and y. And we knew that the perimeter was 2x plus 2y, and that the area was x times y. Now, using this area constraint function, we were able to rewrite the dimension y in terms of x and subsequently express the perimeter in terms of only x. Now, this step is convenient when we go to evaluate the derivative and find the critical values for our problem. Now, upon doing that, we take the derivative with respect to x, which yields the following result. And we know that when we're dealing with a problem where we're trying to find the critical values, we're going to set the derivative equal to 0 and solve for which values of x, those critical values, that would make the statement true. So in doing this, we set the expression 2 minus 2a over x squared equal to 0, which is the same as saying 2 is equal to 2a over x squared, or 2x squared is equal to 2a, and we see that x squared is equal to a, which is the same as saying that x is equal to plus or minus the square root of a. Now, since we're dealing with finite lengths, we don't really want to include the negative value here. It just doesn't make any practical sense for this problem. So we're going to eliminate that, and we're going to say that x is simply equal to the positive square root of a. Now, that would indicate to us that y must also be equal to the positive square root of a, since we know that x times y is equal to a. And this is the value that we want to check. We want to ensure that this is a minimum, in fact, and confirm that. Now, in order to do that, we're going to take the second derivative. I'm actually going to start a new page here. And we're going to begin with our first derivative here, like that. And when we take the second derivative, it will allow us to perform the second derivative test, which is a nice way to find out the inflection points that may exist in our function, or to test for the minimum or the maximum, or if we have a saddle point. And the way we're going to do that is by the sign of the second derivative function when we evaluate that function at our critical point. So first we want to construct the expression for that second derivative. Now when we take the derivative of 2, we have a constant, so that's going to be 0. And when we take the derivative of the second expression, I like to rewrite this. I'm actually going to rewrite it up here. I like to rewrite this as 2a times x to the minus 2, and that just helps me visualize this. Plus, I believe it really gives a more straightforward application of the polynomial rule for differentiation. Here we're going to bring down this minus 2, which we could see is going to give us a positive sign there. Multiply the 2 that we already have. That's going to give us a 4 times a, and we're going to drop the power by 1. This is the same as 4a over x cubed. So this will be the expression for our second derivative in terms of x. Now what we're going to do then is plug in the critical value that we solved for, that being x is equal to the positive square root of a. So in doing that, we say that evaluating the second derivative when x is equal to the positive square root of a, that's going to give us, in the bottom here, that's going to be a raised to the 3/2. Now we can simplify this further. And we're dividing a to the 1 divided by a to the 3/2. That's the same as subtracting the power. So what we're going to have is a to the minus, a to the minus 1/2 here. Like that. So this is going to be the same as 4 over the square root of a. Now, since we know that a is a positive value because we are dealing with a finite area, something that has some practical size to it, we're automatically confirming here that this value is going to be greater than 0. In this context, the notion of a negative area really has no meaning, so we restrict our measured length, our metric, if you will, is restricted to positive values. So we know that x is positive, y is positive, and therefore the area is going to be positive. We divide a positive number by another positive number, and we have a number that's greater than 0. And what this tells us, as by the second derivative test, is that our value is, in fact, our critical point is, in fact, a minimum of our function. And the reason for is that the second derivative sort of indicates the concavity of the plot of our function. So when we have a positive value for the second derivative, we're looking at something that's concave up. And this point down here would be our critical value. And that critical value, we can see that if we travel a little bit in either direction, we're going to increase the value of our function. And what that says about this point here is that that point is going to be a minimum because, again, as we go in either direction, we're increasing that value. Now, conversely, if we had a negative value when we evaluate our second derivative at our critical point, we're going to see that as we travel in either direction from this critical point, we're going to end up decreasing the value of our function, and that indicates a maximum at that location. There's also the case in which this is directly equal to 0, and that's when we end up with what we call a saddle point, where the direction we travel will determine whether or not we increase the value of our function or decrease the value of our function. And that really is not a determinate second derivative test. It's not very conclusive. However, in this case, we do have something that's going to always be greater than 0, so we can say that this is, in fact, a minimum, and we confirm the result that Professor Doru had alluded to. We also know that we can also check for further inflection points if we examine this expression for the second derivative. And these inflection points are going to be locations where the second derivative is equal to 0. Excuse me, I miswrote that. So these inflection points are going to be locations where this expression is equal to 0. And what we find is there's not really going to be any locations where this is equal to 0. It's kind of intuitive to see, as we have we have 4a, which is a constant, divided by our x cubed. We know that this can't be 0. We know that no value for x here is going to yield 0, except if we consider the limit that x goes to infinity. But again, we're trying to deal with practical sizes here because we're constructing a finite rectangle. And what that says to us is that there's no other place along the interval of this function where we're going to have this an inflection point that's going to change the concavity of our function. This indicates that our minimum that we found up here is in fact a global minimum. This is the absolute minimum. Any values of x and y which differ from the ones that correspond to our critical points, so that being any value of x and y that are not equal to one another, are going to yield a result where the